Welcome everyone. Today I'll solve some question of real analysis from IIT JAM 2023. So without wasting any time, let's go to the question. First question: A and B a sequence of real number defined by n is 1 if n is prime and is minus 1 if n is not prime. And we construct another sequence Bn from an, Bn equal to an by n for all natural number. Then the first option is an is convergent but Bn is not convergent. Both an and Bn are convergent. Both an and Bn are not convergent. And last option is an is not convergent but Bn is convergent. So question is asking about the convergence of the sequence an and Bn. So first look at the sequence Bn. Bn is an by n for all n in n. So mod of Bn is mod of an by n for all n in n, and mod of an is always 1 for every n in n, because an is 1 or minus 1. So this is equal to 1 by n for all n belongs to n. Now if we take limit as n tends to infinity, then we will get that limit n tends to infinity mod Bn is 0. So limit n tends to infinity Bn is 0, because if mod of Bn, if Bn is any sequence and mod of Bn goes to 0, then Bn also goes to 0. We can prove it easily. Just observe that mod of Bn minus 0 is equal to mod of Bn minus 0, and this is less than epsilon for all n greater than equal to some k, where k is some natural number. Suppose an is Cauchy. Then for epsilon equal to half, there exists n belongs to n such that mod of an minus am is less than half for all mn greater equal to n. Now since there is infinitely many primes, there exists a prime p that is greater than n. Now mod of ap minus a to n is equal to mod of 1 minus minus 1, which is equal to 2, which is not less than half. A contradiction. So an is not Cauchy, and therefore we can conclude that an is not convergent. So option 1 says an is convergent but Bn is not convergent, which is not true. Option 2 says both an and Bn are convergent, which is again false. Option 3 says both an and Bn are not convergent, which is again false. Option 4 says an is not convergent but Bn is convergent. This is true. Let's move to the next question. In this question, two sequences are given an equal to 1 plus 1 by n to the power n, and another sequence is bn is equal to n cos n factorial pi by 2 to the power 10. Now the option asks about the convergence of the sequence n and the boundedness of the sequence bn. So we have to check whether the sequence an is convergent or not. An is 1 plus 1 by n to the power n. We can show that an is monotone increasing and bounded above. Arithmetic mean of finite number of positive real numbers is greater or equal to the geometric mean of those real numbers. Consider n plus 1 positive real numbers. 1 plus 1 by n, 1 plus 1 by n, and 1 plus 1 by n. These are n times, and the last number will be 1. Now apply this. Am is greater or equal to gm. Then we have arithmetic mean of this n plus 1 positive real number will be n into 1 plus 1 by n plus 1 by n plus 1, which will be greater or equal to 1 plus 1 by n to the power n by n plus 1, and which implies n plus 1 plus 1 by n plus 1 is greater or equal to 1 plus 1 by n to the power n by n plus 1, and this implies 1 plus 1 by n plus 1 is greater or equal to 1 plus 1 by n to the power n by n plus 1, and from which we can easily obtain that 1 plus 1 by n plus 1 to the power n plus 1 is greater or equal to 1 plus 1 by n to the power n, and this implies an plus 1 is greater or equal to an. Now it will be an exercise to prove that an is bounded, and since an is monotone increasing and bounded, therefore the sequence an is convergent. Therefore option 1 and 2 cannot be true. Now consider the sequence bn. Bn is n cos n factorial pi by 2 to the power 10. Now for n greater than 2 to the power 10, we get that bn is n cos n factorial pi by 2 to the power 10, and since n is greater than 2 to the power 10, n factorial by 2 to the power 10 must be an even integer. So this will be cos of some even integer into pi. So this will be 1. Therefore it will be n. Therefore we can easily say that bn is not bounded. Therefore option 4 is not true and option 3 is true. Let's go to the next question. Question number 12. In this question, two sequences are given. An is equal to sine of 1 by n cube and bn is sine of 1 by n, and the options ask about the convergence and divergence about the series summation an and summation bn. To check whether the sequence summation an or summation bn is convergent or divergent, we will apply a limit comparison test. So take the sequence an. An is sine of 1 by n cube. Now let un equal to 1 by n cube for every natural number n. Now the limit of the ratio an by un is limit n tends to infinity sine of 1 by n cube by 1 by n cube. This is equal to 1. We can obtain this limit by using sequential criteria of the limit, and the limit x tends to 0 sine x by x is 1. Now by limit comparison test, the series summation an and summation un converges or diverges together. Now since the series summation un is convergent, we can conclude that the series summation sine of 1 by n cube is convergent. Now come to the now take the sequence bn, which is equal to sine of 1 by n. Let bn be the sequence 1 by n. Now calculate the limit of the ratio bn by bn, which is a limit n tends to infinity sine of 1 by n by 1 by n, which is again 1. We can obtain this limit by using the sequential criteria of the limit, and the limit sine of limit x tends to 0 sine of x by x equal to 1. Again by limit comparison test, the series summation bn and summation bn converges or diverges together. Now summation bn is divergent. Therefore we can say that summation sine of 1 by n is also divergent. So option 1 is not true, option 2 is also not true, option 3 is also false, and option 4 is correct, because an is convergent, the series summation an is convergent, and the series summation bn is not convergent. Let's go to the next question. In this question, a sequence is given. An is 1 plus 2 to the minus 2 plus dot 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 n to the minus 2 by n, and this is for every natural number n. And the options ask about the convergence of the sequence an and the convergence of the series summation an. To check whether the sequence an is convergent or divergent, we have to recall a theorem. I am writing the theorem. If xn be a sequence in R and limit n tends to infinity xn is L, where L is a real number, then limit n tends to infinity x1 plus x2 dot 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 xn by n is L. Let xn equal to 1 by n square for every natural number, then an is equal to x1 plus x2 plus dot 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 xn by n, and limit n tends to infinity xn is 0. Therefore, limit n tends to infinity an equal to limit n tends to infinity xn, which is 0. Therefore, the sequence an is convergent. Now I will check the convergence of the series summation n equal to 1 to infinity an by applying limit comparison test. Let bn equal to 1 by n for all n belongs to n. Then the limit of the ratio an by bn is equal to limit n tends to infinity 1 plus 1 by 2 square plus dot 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 plus 1 by n square. This is equal to the sum of the series n equal to 1 to infinity 1 by n square. Since the series summation n equal to 1 to infinity 1 by n square is convergent, and this is a non-zero positive real number, therefore the series summation an and summation bn converge or diverge together. Now summation bn is divergent, and therefore the series summation an must be divergent. Therefore the sequence an is convergent, but the series summation an is divergent. 1 is wrong, 2 is again wrong, 3 is true, and 4 is false. Let's go to the next question. In this question, two sequences of real number an and bn are given such that they satisfies these two conditions. Mod of an minus an plus 1 equal to 1 by 2 to the power n, and mod of bn minus bn plus 1 equal to 1 by root n, and this holds for every natural number n. Then the options are asking whether the sequence an and bn are Cauchy or not. For m greater than n, am minus an equal to am minus 1 plus am minus 1 minus am minus 2 plus dot 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 plus an plus 1 minus an, which is less equal to, by triangle inequality, am minus 1 plus am minus 1 minus am minus 2 plus dot 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 plus an plus 1 minus an, and this is less, and this is equal to 1 by 2 to the power m minus 1 this is equal to 1 by 2 to the power m minus 1 plus 1 by 2 to the power m minus 2 plus dot 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 1 by 2 to the power n. If we simplify this expression, then we will get 1 by 2 to the power n into 1 plus 1 by 2 plus dot 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 1 by 2 to the power m minus n minus 1, which equals to 1 by 2 to the power n 1 minus 1 by 2 to the power m minus n by 1 minus 1 by 2 equals to 1 by 2 to the power n minus 1 into 1 minus 2 to the power m minus n, and this is less equal to 1 by 2 to the power n minus 1. If we take limit as n tends to infinity, then we can see that mod of am minus an goes to 0. Therefore, the sequence an is Cauchy. Now I will show that the sequence bn satisfying this condition may not be Cauchy. To prove this, we have to construct a sequence bn that satisfies this condition, but bn is not Cauchy. So let bn equal to 0 if n equal to 1 and is equal to 1 plus 1 by root 2 plus 1 by root 3 plus dot 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 1 by root n minus 1 if n is greater or equal to 2. Then we can easily check that bn plus 1 minus bn is 1 by root n. This holds for every natural number n. Now see that the sequence the series summation n equal to 1 to infinity 1 by root n is divergent, and from this we can easily get that the sequence bn is also divergent, and therefore the sequence bn cannot be Cauchy. Therefore the answer will be the sequence an is Cauchy, but the sequence bn need not be a Cauchy. So option 1 is wrong, option 2 is correct, option 3 is wrong, option 4 is wrong. Thank you for watching.